as one integral. So we'll come back to that, I promise, in the next minute or two. We already talked about that yesterday. What functions are integrable? We said continuous, and actually we said it's actually more, we have more liberty than that even. We can even integrate things like the greatest integer function. But certainly a low bar would be continuity. So the first thing I want to highlight is order of integration, which is the thing that came up in G. So I told you we'd have a right away answer to that. So here we go. So the order of integration goes like this. What did you say the answer was 12? Was it 12 or negative 12? Did we decide? No.
Yeah, 12.
It is actually 12 because you're going underneath the x-axis and you're going backwards. This idea of integrating backwards generates the same thing that you get if you integrate forward, but the opposite, okay? And I'd like to ask then also, like, why?
Which one were you talking? So G was 12?
It's positive 12 is the answer to G, actually. Yeah.
But it's
Julian?
9.
What is? dx is negative, right? So if you're integrating f of x dx, remember yesterday, this is a big surprise, was that if you're integrating a function that drops below the x-axis, during that time you get a negative value for the integral. But then we said, oh, actually, that's not a huge surprise maybe. It kind of makes sense based on the definition. What are we doing? We're adding up rectangles. You know, we're getting f of x values times delta x, and f of x is a negative thing, and so when we add up a bunch of negative things, we get something negative, and oh, okay. I guess I get it. And then Julian said, now, what if delta x is negative? If f of x is above the x-axis, and delta x is positive, then we get something positive. But if delta x, each time we're calculating those rectangles, we have f of x, which is positive, times delta x, which is negative, then we get a negative answer, even if we're integrating above the x-axis. If we're integrating, like, backwards from b to a. So what if f of x and dx are both negative? That is, what if you're below the x-axis and you're integrating from right to left? Well, then you get something positive, which is g from the 1 up, and which is exactly why you get 12 there. Did you have another question, Morgan? Sorry.
But you were going from 9 to 15.
15, 9. On G?
Yeah.
From 15 to 9. So that's from right to left.
Oh.
Yeah, so that is this situation exactly. So is that a good enough explanation? Which property, what's the property I'm going to list right here, right now? I have the title here of 0. Yeah, A to A, very good. Yes, from A to A is 0. And I have nothing really to say about that, so I'm going to move on to the next property. I don't know if I even want to, I don't know that there really is even anything to explain or prove. I think that makes sense. Here's one that we haven't discussed, but it's powerful and useful, and it's super important. So what does that say? I had the label it constant multiple. What have I done here? Interpret for me the symbols. Okay, that's true. And what do we do with what can be done with it? Yeah, it can move like osmosis through the cell wall. Okay. It can come out of the integral in a similar fashion to how we dealt with derivatives, right? Like, you know that if you have a constant times a function, the derivative of that function is the same as if you take the derivative first or multiply by a constant first. You can do it in either order, right? You can pull out the constant, take the derivative, and then afterward multiply by the constant if you like. So we're saying a similar thing can happen for integrals as well. Why is this one true? Can someone explain why this is the case? Yeah. Yeah, okay, can you say more?
It's all proportional.
What's proportional? Can you say things, can you fill in what it means and stuff like that?
No.
Go ahead, really, let's sound off.
So I think it's because of the distributive property, because if we're adding up a bunch of terms that all have something that can be factored out, and just distribute it out. So that's the
Yeah, this is like a glorified way of saying this is the distributive property, really. I mean, remember where we came from, right? What is this integral? Go back to Riemann sums from this past week, right? Really, this is a sum and imagine this sum. It would be, if you were computing all the heights of the rectangles, you know, you'd have like k times the function value plus k times the function value plus k times the function value. Do you think you could just factor out the k? Absolutely, right? It's just, it is just the distributive law. The sum and difference, we can take f of x plus g of x inside the integral and separate it into two integrals. So if you're integrating x squared plus 2 from whatever to whatever, instead you can do the integral of x squared plus the integral of x, or whatever, an integral of 2. You can break it up into two separate integrals. Or go the other way. So now I'm ready to return to answer your question now, Piper, from the homework last night. So you already said that you could write the integral, the desired area over here as the integral from 0 to 2 of 2x dx minus the integral from 0 to 2 of x squared dx. That's how you probably wrote the answer, right? And then how could you write that?
The first one and then the second one after 1, so I
Yeah, and you just left that blank. But now you can go back and fill it in. Oh, maybe you said it and you were fine. Yeah, and well, so no, now we'll just come out and say that you're allowed to do what you probably already did do. And that's what? So this is the property we're just now talking about and highlighting. Why is this true? Why is this true? Again, maybe actually think about writing out these sums. Can you imagine, like, say we're doing x squared plus 2 or something like that, like we were just saying, x squared plus 2 from 0 to 4. Say we want to, if we were, well, this is not a proof, but say we're doing like LRAM 4 on this, wouldn't that be 1 times 0 squared plus 2 plus 1 squared plus 2 plus 2 squared plus 2 plus 3 squared plus 2? But couldn't you equally say, do you see what I'm about to do? Couldn't we also say that's 1 times 0 squared plus 1 squared plus 2 squared plus 3 squared plus 1 times 2 plus 2 plus 2 plus 2? You see what I'm saying? I could have done them separately. I could have done LRAM 4 on x squared and LRAM squared on LRAM 4 on 2 and added them together, right? And so why does this end up being the same as that for a Riemann sum? Well, because of like algebra, right? Like because of the commutative and the associative properties. Those are the words I use maybe. So that's really what this is saying too, is that these sums can be rearranged. That's all. I don't know if that's the world's best example, but that's what's, but that's what I'm thinking of as I do that. Again, a really formal proof of this would need to maybe use the kind of the summation notation approach that we developed the other day when we first introduced this notation. And we will delve more into that connection very, very soon in a deep way. This one, can you just stare at it for, I don't know, 30 seconds? Until it becomes like, oh yeah, of course. Yeah, until you say like, duh. Stare at that until it's like, oh. That's going to be a problem. Did everyone, has it become self-evident to everyone? What can you see? What? Who's that? You want to come here?
Yeah. Okay.
There's not much to say about that one, really, right? In fact, you're already using it without even really thinking about it as a property, like in parts, when we were doing A and B and C of the warm-up today, right? Isn't C the sum of A and B? Right. Good job.
I have a question. For like the constant multiple, what's the difference between having the k next to the f and having the k outside of the f, outside of this s?
Well, they're the same thing. Is the answer is no difference. is the answer.
Yeah, but
like, why would you care?
Yeah, why would I care?
Yeah, so the
About
homework will
moving the
highlight that a
thing.
little bit, but, and some of the examples here. But also, when we actually do some integration later as well, it'll turn out to be a convenience, I think, a lot of times. Just like when you're taking derivatives, right? You don't want to involve it. It's easier to do the math and then multiply afterwards.
Is this the thing we did the other day where you put like 2 on the outside and then you put all the things on the inside?
Yeah, exactly. Like,
Okay.
like anytime we can do work and then later multiply it, that might be, it has the possibility of being easier. All right, what are we doing on this one? Some non-properties. Okay, so just from my vast mathematical pedagogical experiences, students think that these are things you can do, and so I don't normally tell you put things on the slide that are not true. But here are 2 things that are not true that students are tempted to do sometimes. Let this not be you. Notice the not equal to, not equal to. All right. So after getting carried away with all these properties, you might just be like, well, everything I think that works, works. Well, no, hold up. I know all the other properties seem very nice and are very intuitive and make sense, but not everything that you wish were true is true.
Gotcha.
Oh yeah, that makes sense. That makes sense. That wouldn't work.
Okay, good.
Wait.
Yeah. Alex.
No, say it.
No.
Say it. Say it.
Never mind. It doesn't have to say it. Yeah, I don't have to say it.
Yeah.
Thank you.
Uses okay.
One of the black ones.
Stop.
One of the black ones.
See, you want
But
to.
like, I have one of those, so you can see one of the black ones.
There really isn't one. The best answer to that question will come in the next unit, and the answer will be like something called integration by parts, which has a little bit of help for us on this. But
Could this be like a question on sense like divide? Oh wait, can't do that.
maybe, yeah.
You
I
can
guess.
do it, but they're not.
No.
All right, let's practice. Here we go. I've got a couple. The rest of this is just now us doing some examples. Take a second to do these, and we'll call some people. I don't know. 2 minutes.
The second one. None of these work. Numbers don't work. Oh. Numbers don't work.
No calculator, no calculator.
So you haven't learned NG. You haven't learned.
Well, how do you? Well, hear from some people. Remember, there's I guess I don't need this anymore. Remember, you can think about geometry on all these,
Oh,
right?
yeah.
So think about lines and circles, just like the warm-up.
I don't understand why the square root of f minus x squared. I mean, yeah. I don't understand why that's a circle. What is
Why this is a circle?
Can you write the formula of the circle for me?
So can you convince yourself?
I forgot what the formula of the circle is.
How about you rederive it yourself? So that's a semicircle, right, or something, or a radius 1.
Why is that a circle?
How about you mess with it until you're convinced that that's the circle?
If I don't know what circle function.
Euro.
Not function.
Well, what must be true? What must be true about, so let's say we have a circle centered at the origin of radius 2, so what must be true about any point if it's going to be on the circle? What must, how do I know if I told you that, I think that, I don't know, 2.5 comma 1 is on the circle. How would you check that I'm right? check that I'm right. Check whether I'm right or not, please. What must be true?
2.5 squared plus 1 squared, and then you take the square root of all that, and that needs to equal 2.
And that needs to be equal to
Yeah,
2. Good. So in general, what's the test if I say I think that this point x y is on the unit circle is on this 2 unit circle?
Square root of x squared plus y squared equals the equation.
Right. So so this describes all the points. If x y satisfies this equation, then that's the picture.
So,
Right?
and that one is the radius x or y?
Now what?
And that y equals square root of 1 minus x.
So another way of saying what you said is that x squared plus y squared better be equal to 2 squared, right? So this is the equation of a circle of radius 2. This is another way of writing that, though. Right? Can you solve this for a y?
Oh, okay. So x minus 4. Yeah, x be 4 minus x.
But of course, because it's a function, the square root is part of the problem, right? Plus or minus, we only do the top half of the circle.
Okay, I got you.
All right, here we go. Let's call on some people. You give me the answer when I call on you. Is Mara in the house?
Say something that makes
Mara. Hey. 7. Agree? Caduce, is he in the house? Peter? Cedric? B. What'd you say? Sorry. 4 pi? Right? 2 pi. Wait. Why is it 4 pi?
I plugged 2 into pi r squared.
Alright, so 2 into pi r squared does give 4 pi.
Divided by 2.
Oh, so are you revising your answer? You say it's 2 pi. Okay.
It's negative 2.
Wait, there's still detractors?
Oh man.
Why is it?
It's going backwards to negative 2.
Oh, because we're doing like a PowerPoint on the properties of integrals? Oh, that's why. Yeah, just pay attention. We're going from 2 back to negative 2. Okay. What about C? Is Michelle? Olivia. Oh, you don't have it. We'll come back to you in a second. And you want to volunteer for that one? No, that's Olivia's. And D, Alex, can you help me on D?
6 pi.
6 pi?
Yes.
How'd you come up with that?
Wow. It's like the property share, so that you can take the 3 and
Move it out. And then we know it's going the right way.
Wait, are you?
We work together.
yeah, it's the ends on our arm.
Okay, well, I'm hoping that
Yeah, I'm trying to.
you know.
Yeah, I do.
Yeah.
So the property just shows you can take the 3 and move it outside of the integral. So you solve for 4 minus x under the integral of that first, and then you multiply by 3, and so you get 2 pi, and then you multiply it by 3, and you get 6 pi.
I think I agree with you on that. And Olivia?
Yeah.
Yeah, 0.
Self-love at its finest.
Good. Amy, let him be his own man, okay?
You literally just yelled at me.
Okay.
Right.
Here we go.
Thank you for
So
backing
no.
up.
There are 2 worksheets that Haley's gonna, Rosie's gonna be bringing to you.
Both of them. Sorry, I have to go.
What? How many are there?
2. Actually, sorry, I took a 0 at the end. There's 20.
Dan Boyd.
No.
See, you got the good sarcasm to be a teacher too. That's good, Rosie.
Hey!
I should sort him out now. Can you, is Jack getting home? Oh no, he was here last year.
Yeah.
Go back to sleep, sorry. Isha is not here.
It's only when you find him in your reading, but like,
It's not really cool. Maybe it's like a mystery.
we're gonna put the next grade on you.
Is there a guy?
I just didn't go for it.
What's anyone? I think we might need some advice on this one. We might need some advice on this one. Anyone? Anyone need? Can someone give us a weigh in on this? What? Anyone have a way in at all on this? Or is this impenetrably difficult?
Well, you can make it f of x, the integral of f of x plus the integral of x, and then that becomes 25 over 2.
So wait, hold up. So the first thing you said was what?
Oh, f of x, the integral of f of x, and then the integral of x.
Yeah, so let's just start by that if no one has said that yet. Certainly the thing we're seeking is also equal to the integral of f of x plus the integral of x dx by one of our properties. And then now you have two new problems in life, both of which you can solve separately and add together. So separate this into two using the property 3, the 4, property 4 for our list. Forget, I think what it's right? Yeah.
I want to make sure that I said everything.
And then solve each of those separately.
Wait, no, that would be 1 to 5. 0 to 5.
Oh, and then X.
Oh, wait, no, I'm being dumb. That's what I think.
All right, Amy, when you're ready, can you finish this off for me here? What do we do next then?
I was.
Don't work on the worksheet yet, if you don't mind. Could you focus up here again? Sorry, we passed that out just a second too early.
Okay.
Classic
So the
teacher
second
mistake.
one is 5, yeah.
Say it again. Wow. Maybe, yeah.
Oh, would it be 15?
Well, what is this first?
That's 10.
Yes, that's 10. Let's all just say that. Because it's given, there's no debate about that. It's given. All right, the debate here now is what is this integral? It's not 5, though. What are you integrating? I think Alex is right, even though you don't want to listen to him. Visualizing it will help, right? Think back to, our geometric approaches that we've been taking. What are we integrating? What are we actually trying to find the area of? A triangle, yes. So what's the base? What's the height? Do you guys agree? 12.5. So y equals x from 0 to 5. The triangle with base 5 and height 5. Can you visualize it?
Yeah.
Okay. So what's the answer, Amy? All right, can you bear with me doing one more? I think this is a fun problem. I promise. Nope.
That's such a shame.
Everything's homework. How many problems is that?
It took me 10 minutes.
They're really quick. Here, I'm going to come over. I'm going to do the first problem for you. Good. You're welcome. You're welcome. That's just the kind of guy I am, though. The answer to the first problem is 0, everybody. Have a great weekend. Go Rockets.
One of them on the first one.
I want that.
then me and Ellie gonna get on the
Yes, not that one, right? Not enough information.
Do you think I could be the next great best scientist who also yeah? Yeah.
Absolutely.
So what I'm
Yes.